Hey folks, let's get back to talking about functions, and I want to talk about inverse functions. We've already talked about inverse relations, and I'm not going to change anything that we've said. You know, if you have a ordered pair AB, then the inverse relation means you have the ordered pair BA. What I do want to talk about is when that inverse relation becomes an inverse function. Okay, so let me be real careful about this. When we use the notation f to the negative 1, which is horrible notation, by the way, it's not 1 over f, we are referring to the inverse relation, f inverse. We are not guaranteed that f inverse is a function. And that's a slight departure from what we've done in the past, because typically we only use that notation if we know that we have an inverse function. That's an algebra kind of thing we did back in college algebra or whatever it was. But we're being a little bit more abstract than that. We're talking about relations that have certain properties. You can always have an inverse relation. Okay. The question is whether or not that inverse relation is a function or not. So let's talk about what has to happen in order for that to be a function. And if you'll excuse me for just my pen's going dry, I'm going to go. I'm just going to change that out real quick, and I'm going to pause for just a moment. And I am back. All right. So the other thing that I didn't do in part 1 of today's lecture is I didn't work a lot of examples of proofs with you, so I want to do some of that too. I was really kind of waiting until we got to this part, because this is where the really kind of cool kind of things are. So let's establish one thing, and that is that if f going from A to B is a function, then f inverse going from B to A if and only if, and if you remember what happens here from your old college algebra days, f had to be 1-to-1, right? And also onto, but we kind of handled that by limiting the range, right? So that was less of an issue, but in this kind of abstract thing we're working in with A and B, we need f to be a bijection, which means 1-to-1 and onto. So let's actually go through and prove this. It'll be a good example for you in some of the other problems that you're going to work, and it'll also establish when we can find an inverse function, okay, which is a good question. So we've got, we'll start by, no matter what happens here, f is a function, okay, so this part I'm not worried about, but let's start by assuming that this is a function and proving it this way. We'll have say if this is a function, then we'll prove that it's 1-to-1 and onto, and then we'll turn around and say, okay, let's say it's 1-to-1 and onto, show that it's a function. Okay, so let's f inverse, which goes from B to A, be a function. Okay, and what we want to do then is show to be a bijection, it's got to be one-to-one and onto, right? So let's tackle the onto part first. Let's consider, now F goes from A to B, so I need to take some element out of B, just a general element out of B, okay? So let's consider a just basic element B in the set B, okay? And what I need to do is show that that has an image, I'm sorry, a pre-image, or that B is the image of some value in the set A, okay? Well, since F inverse is a function from B to A, then there exists some unique element A in A such that F inverse of this B is A. There can't be two of those A's for that B, there's only going to be one because it's a function. Well, F is an inverse. So we basically, in F inverse, we've got the ordered pair B comma A. Well, in F then we've got the ordered pair A comma B. So then F of A equals B. Thus, and that's what we needed to show, was that I could find an A that gave me the B. So thus, F is onto B. Okay? Now let's tackle one-to-one. And so what we do here is we say, all right, let's assume that there's a couple things in A, the set A, that when they get over to the set B, you know, to F of this and F of that, they're equal. Okay, this is how we prove one-to-one. So suppose there exists A1 and A2 in the set A such that F of A1 equals F of A2. Now, the goal here, if you remember what one-to-one means, is that if this happens, one-to-one means that that A1 and that A2 would have to be the same element. Okay, they'd have to be equal to each other. All right. So since F inverse is a function, well, if you take two things that are equal and you pop them into a function, you get the same answer, right? So if x equals A, f of x equals A, then f of x equals f of A. That's the deal. All right. So then f inverse of f of A1 is going to be equal to f inverse of f of A2. But remember what inverses do, right? They undo the ordered pair. So whatever A1 goes to in B, F inverse would turn around and take that B and bring it back to A1. Right? So since is an inverse, then A1 equals A2. Okay? Thus, F is 1 to 1, and F is a bijection, since you've got both. Okay? Now, let's go the other way. Suppose F is onto and 1 to 1. Okay? To show it is a function, okay, I need to say, all right, we can always find a, well, let's see, I got to go the right way. I would need to show that F inverse is a function, right? So that means if I take any kind of element, F inverse is going to go from B to A. So if I take any element in B and apply F inverse to it, I get a unique answer in the set A. Okay, exactly one answer, and it has to work for every element of the set B. Okay, so I think you see where we're going with this. Since F is onto, then for each B in the set B, there exists A in the set A such that F of A is B. Okay? And here's the other thing. This A, there can't be 5 or 6 of them, right? Because F is 1 to 1. Okay, I think I can just say that, but let's just think it through. If there was a couple of things that were B, then I'm back up here, right? And 1 to 1 means that those two things would be equal. Okay? So I'm going to say since F is 1 to 1, then A is unique. Okay? So that means then that if I look at the inverse, I've got the ordered pair AB with F. This would have the ordered pair BA. Okay? And that A being unique is important, right? The fact I can do it for each B is important, and the fact that A is unique is important. For each B in the set B to an unique A in the set A. Thus, F inverse is a function. So we went this, if this, then this, and then we went if this, then that. Therefore, the statement holds. Okay? All right, so that's the requirement, is that in order for us to talk about F inverse and have it be a function, we have to be talking about a 1-to-1 and onto function F. Okay? And if that happens, we'll say that F is invertible, that we can then find an inverse function for it. Okay? All right. Take the time, look that over, and kind of see that we're using a lot of the same strategies we've used before. Okay, it's just with some different concepts, the concepts of onto and one-to-one. Okay, and also with function, which I guess is kind of new. Okay, but this business of proving a biconditional statement by proving it one way and then proving it the other way, we've done that to death, right? Okay. All right. So not only is that show that we've got a function, but anything that behaves like a inverse, that will be an inverse. Okay, so let me state clearly what I'm talking about here. Suppose f going from a to b is a function, and g going from b to a is a function. Where, if I look at f composed with g, now where does this end up? We take something, f lands in b. So when this is all said and done, I end up with something in the set B. But now G starts with B, right? So it takes something in B and gives me that back. Okay? For all B in the set B. And if I look at it the other way, G of F. Okay, now this it starts in A, goes to B, comes back to A, and gives me the same element for all A in the set A. Then F has an inverse function and that inverse is just G. Okay? So what it's really saying to us here is that anything that behaves like an inverse, it's an inverse. Okay? And okay, so we need to show two things, right? We need to say, okay, let's make all these assumptions. Then it's an inverse function, has an inverse function. Well, I'm going to defer back to the theorem we just proved, right? Just a second ago. If it's one-to-one and onto, I get an inverse function. Those are easier things to prove, perhaps, right? And then show that for every ordered pair that I have in G, and it's also in the ordered set of ordered pairs that make up F inverse. Okay? So let's set about here on our proof, and I'm going to start with onto. Okay? To show that it's inverse function, I'm going to show it's onto and one-to-one. Okay? So onto, I take a general thing in B and show that I can find an element in A that gave me that B. Okay? So consider a general element B in the set B. Okay? Then I know, because of this statement right here, since F of G of B is B, that there exists G of B think where G of B is. This is in A. Such that F, well, I just said this, G of B gives me, okay. So we can call this something cleaner if you want to. Okay, just call it maybe A. It's definitely in the set A. Okay. Then that's it. That's all I got to do. Then F of A is B, and that means that F is onto. Remember, onto means, oh, you give me a general B, I can go back and find an A that satisfies F of A equals B. Okay? So we got onto. Now let's tackle one-to-one. So again, let's suppose, this is exactly the way we did the other proof just a second ago. Suppose that I've got a couple things here, A1, A2, and A, such that F of A1 equals F of A2. Now what I have to do to show that it's one-to-one is I have to show that A1 and A2 are equal. Okay? Well, remember what G does up here. G takes this F of A and turns it into A for all the A that we have in that. Then G, now G's a function, so if I apply it to two things that are equal, I get the same thing. So G of F of A1 would equal G of F of A2. And then, because of this property right here, this is A1 and this is A2. Thus, F is 1-to-1. Therefore, by our previous theorem, the one we just did, F has an inverse function. Okay? All right. So now we have to show that F inverse and G are the same thing. Okay? Well, this goes back up to this statement. Okay? And it also goes to what inverse is. Since F inverse, or F to the -1, is an inverse function. Now, to show, remember G goes from B to A, so I have to start with something in B, okay, and then it will take it to A, okay. But in particular, let's see, B. Yeah, okay, I got it. Yeah, so for general B, right, we know this is true. F of F inverse of B would have to be B. Okay? And then from above, oh, and this is for all B. Sorry. For all B in the set B. From above, F of G of B equals B for all B in the set B. That means they're equal, right? Then F of G of B equals F of F inverse of B. Okay? But remember, F is 1 to 1. This means, and this means, so G, and this is because since F is 1 to 1, then G of B equals F inverse of B for all B in the set B. Okay? Thus, G and F inverse, basically what you're saying is they have the same ordered pairs. Right? You put something into it, you get the same thing out every time for every B. So, there you go. Alright. That's just a little flavor of the kind of things we'll be having you prove. The other kind of thing they do is they look at, that I'm going to have you do, is having you look at images of sets and showing how the different set operations are kind of maintained through the functions. Okay, so what I mean by that is, here's another example. For a function f that goes from C to D, where A is a subset of C and B is a subset of C, show that F of A intersect B is a subset of F of A intersect F of B. Now, when I warned you I was coming with this, I told you it's a lot of the same stuff we've done. These are sets, right? When we talk about F of a set, that's all the things in the image of that set. So that's a set too. Okay? So if we want to show that this is a subset of this one, we have to take, it's the same old stuff we've always done. Take something out of here, right? And show that it is in here. Now, F of this business, right, ends up in D. So if it helps keep it straight, maybe you let, here's our proof. Maybe we call it lowercase d just to keep track of it. So let D be an element of F of A intersect B. Okay? Now, what does that mean? It means that D is in the image of A intersect B. There's something in A intersect B that gave us D. Okay? So that means then there exists, and I'm going to call it, I'm going to get away from A, B, and C and D. How about X? In that intersection, such that F of that X gave me that D. Right? D's in the image of A intersect B, so there's got to be something in A intersect B so that when I apply the function, I get D. Alright? Now see if this looks familiar to you. Oh, this X, it's in both A and B, right? Then X is an element of A, and X is an element of B. It's because it's in the intersection, right? Then that tells me that D is in the image of A, right? There's something in A that gives me D, and there's something in B that gives me D. So D is an element of f of B as well. It's in the image because x goes to D both times, right? So D is in the image of f of A, it's in the image of f of B, and that means it's in the intersection, right? Thus, f of A intersect B is a subset of f of A intersect f of B. And we're done. Now, you might say, well, why don't you go ahead and prove it's equal? Well, it's not generally true that it's equal. If f is 1 to 1, it will be equal. Okay, when you think about it, when we talk about, let's say we're trying to go the other way, right? Let's take some x that's in this intersection. That means it's in both images, right? It's in f of A and it's in f of B. That means there's something in A that gives me x, well, whatever I call it. What I call it, x. Something here, yeah, and actually it would be, they're both in D, so I could take D in this thing right here. Then that means there's some x in both A and some y in B that give me D. Alright? I can't assume it's the same thing. However, if it's 1 to 1 and I get the same thing, f of x equals f of y, guess what happens with x and y? Same thing. Okay, so 1 to 1 is very crucial here. If you're trying to prove that it's equal, you got to have 1 to 1. All right, enough of that. Your homework assignment then, wrapping it up out of 6-2, our problems 9 through 14. That gives us a few problems to work on Thursday. I've already kind of conceded the fact that it's going to be very difficult for us to get all our work done, I think, and get our test in by next Thursday, the 10th. It might be best to push it back to 15th anyway. If we get done earlier, we can start with our counting and go right on. But it's just kind of bad timing. I have to be gone after class on Tuesday of next week anyway and Wednesday of next week. So I wouldn't be around to answer questions anyway. So I think I'm just going to make the command decision to go ahead and move our test to the, I think it's the 15th, 16th. Let's look and see real quick. It'd be the 15th. Yeah, 15th. So I think that's what's going to end up happening. We'll take our test on the 15th. Okay. And then after that, we start counting. The counting stuff is interesting, but it goes pretty quick, though. I mean, as long as you're getting it, it goes pretty quick. All right, I will stop here, let you work some problems, and we will tackle these on Thursday. See you.